Next, we have our third keynote speaker, Professor Yasutaka Furukawa from Simon Fraser University in Canada, from the Computer Science Department. Yasu, floor is yours.
Yes, can you hear me?
Yes.
Hello? Oh, great, yes. So let me share a screen and start presenting. See screen 2. Hope you see it now, maybe side by side. Then starting this.
Yeah, we're seeing both the browser and your present. Okay,
yes.
now it's
now
just a presentation. Yep,
great.
Good. Great.
Yes, thank you very much for the introduction. So first, I want to thank organizers for running the workshop. It's a great honor to give a talk. In particular, I'm excited with the fact that the people come from a wide range of disciplines. So this is really special and only possible by the workshop. So I'm very excited. So today, I like to talk about teach computers to design architecture, in particular 2D floor plans. So I usually do reconstruction tasks, which is turn sensor data, say images, point cloud to 3D model. But you know that the GAN is making revolutions in many fields. So I got interested in more generation tasks. And GAN often produce raster data images. So you see realistic facial images. These are fake, but not much on structured geometry generation by GAN. Most of the techniques on the CAD model are usually autoencode VAE style generation. So I got interested in maybe can we use GAN to generate structured geometry, in particular 2D floor plan. So I want to talk about generative model in this talk. And this talk, it's going to be a bit technical heavy. So if you are looking for more higher level talks, I have to apologize for that. I usually give high level talks, but this one is a bit more technical. So first, I want to maybe explain why I should care about this, or why you should care about this problem, by explaining what the workflow of an architect is in making a house design. When architects make house designs, say floor plans, they first start sketching a thing called a bubble diagram. Bubble diagram is a graph where nodes correspond to rooms or spaces, and edges encode their functional relationships. And after they get the bubble diagram, they start placing into the physical space a lot and adding details. They realize certain issues, go back to the bubble diagram, and go to the floor plan and go back to bubble diagram, iterate. And this is really time consuming. I believe in North America, more than 90% of houses do not have a dedicated professional architects to design floor plans. They use recycle the other floor plans in some suboptimal way. So this is important to do. And our task is to make this as automatic as possible. So bubble diagram is given. That's what architects produces. So we take bubble diagram, then generate a diverse set of realistic floor plan samples. So that's a task which we are trying to automate. And today, I will talk about a sequence of 3 papers, which we worked on in the 3 to 4 years. We believe we made some breakthrough in the computational capabilities of floor plan generation. This has been a joint work with my SFU colleagues and also Autodesk research. Before going to some technical details, I'd like to show you what the state-of-the-art system which we developed works like. So you can also try it out later by going to HouseGAN++, houseganpp.com. So this one runs on the Amazon the GPU cloud. So it's automatic. So you see at the left is the bubble diagram. At the right, you see the floor plan generation generated examples. So you can also click more examples and generate. Then we have 3 template bubble diagram here. So 1 bedroom suite, and the system generates, and you can see which one you like. Or 3 bedroom suite, more complicated, and then system generate these examples. And you can also modify the graph here. So this is a 2 bedroom suite. So for example, this is a living room, And there should be a bedroom and also the bathroom. So this bathroom is accessible both from bedroom and living room, kind of a half common, half private bathroom. Then also a bedroom, and this bedroom has a dedicated bathroom here, and also the balcony. So I can maybe add one more bathroom, say add node, bathroom. Maybe I make this bathroom, the edges, is a common bathroom, say for guests. I also want to make a bedroom, have a dedicated bathroom here, like that. So the system generates these examples. Let's see which one looks interesting. Maybe like that. This one doesn't look great. So maybe I click more examples to see I get something good. Maybe here. So in this example, so I have this common bathroom here, a living room and 2 bedrooms. And each one has a dedicated bathroom here and a balcony. And maybe another example. A bit weird, too thin, so maybe it's a failure. So I click more examples. So you can kind of play around with the system to get what you want. So again, common bathroom, balcony, 2 bedrooms, and dedicated bathroom here. And you can kind of make things more complicated, but if you make unrealistic bubble diagram, it starts to fail. So maybe balcony to maybe bedroom here. So now you should have 2 balconies, 1 dedicated bathroom. So you can play around later on HouseGAN.pp.com. So I'll talk about how we build this system. And I said it's a GAN, and I said that bubble diagram is a graph. So which basically defines this pipeline already. So input constraint is a bubble diagram, which is a graph. Then generator generates a floor plan. So this is a GAN. So there's a generator neural network. Then we pass this generated floor plan to a discriminator. It's trying to distinguish generator sample versus the real grounded truth floor plan sample. And I said bubble diagram is a graph. So we represent as a graph of a feature vector. And each feature vector contains a room type with one hot encoding with some noise vector, because this is again, there's noise vector. And in particular, we may want to also maybe contain room size or other property, but to be simple, it's a room type that's associated with each node. And later, we'll also generate doors on doors. And in that case, each edge means a door has also a feature vector. But for this illustration, I just talk about nodes and rooms and ignore the doors and edges. But you can generalize in a similar way. And we generate a floor plan as an output of G generator. And we represent floor plan as a graph of binary segmentation masks, meaning, so this node corresponds to, say, a balcony. So this node is going to have a binary segmentation image. So this is a binary single scalar segmentation image, which contains where the room shape segmentation is. And same thing for the other room. Each node has a binary segmentation image. So we represent a floor plan as a graph of binary segmentation masks, which is passed to discriminator. And a GT, ground truth floor plan, is also represented in the same way as a graph of segmentation masks. And D, discriminator, trying to say true and false. So if you see this, oh, everything is a graph. So why not use graph neural network or GNN? Because you see here and there, GNN is amazing, makes revolutions. So maybe GNN, you take a graph of noise vectors and room type, output graph of vectors, maybe putting CNN decoder, get the segmentation mask and done. It's pretty simple. Unfortunately, this does not work. GNN actually cannot do this task. So the first paper, the message of the first paper is when and how should you use the GNN? Because there are typical misconceptions. CNN requires fixed input dimension and fixed output dimension. So once your input dimension varies, say a graph whose number of nodes, number of edges vary, just think that, oh, CNNs are not valid. maybe GNN, graph neural networks are the choice. That's actually a very bad misconception. So this is the kind of question or misconception which I want to remove in the first paper here. And this paper actually tackles the reconstruction problem, structured reconstruction problem instead of a generation task. So I want to use this reconstruction task to deliver this message, when and how you should use GNN. So this task is you're given an image and then generate a, say, graph representation of building like this. And we did this in 3 steps or 4 stages. We do corner deduction by, say, standard combinate. We enumerate edge candidates by some heuristics. And now, given some numbers of corner candidates, edge candidates, we choose a good, correct set of edges. In this last step, edge selection, this sounds like a very nice GNN task, because the task is to classify each candidate edge to be true or false. And the number of edges, the number of nodes vary per sample. So CNN likely cannot do well. So GNN does everything in one shot. It's very nice. And I use a bit simpler building example to illustrate how this procedure may be like. So I take this building, say 6 corner candidates, and then 9 edge candidates. But this is a real answer. So we want to say these 4 edges are true. The other edges are false, which I want to do. So here I have edges, building edges, and building corners. Every one of them become a node in GNN. So the 6 corners, building corners become 6 nodes here. The 9 edges become 9 nodes of a graph for GNN. And then we connect them if, say, edge is incident to 2 corners. So these are connected like that. So from here seems straightforward. Okay, we have a relational graph for GNN. Maybe initialize features, say by feature extraction. We can use, say, SIFT for representing this feature around each corner. Use any descriptor, maybe edge descriptor for each edge, or you can maybe use convolute. Then use features in convolute, put over these edges to extract. But in whatever way, initialize some feature vectors for each node. Then we do message passing by GNN. Usually matrix multiplication, a fully connected network, or simple MLP in short. In MLP to update feature vectors. And after that, we ask each edge feature vector, just putting some MLP decoder, asking, are you correct? Are you correct? So the MLP decoder output true, false. Then we know which edges are correct. So it sounds pretty straightforward. But again, this does not work, unfortunately. We spend quite a bit of time debugging. This cannot work. And there are a few issues why this cannot work. But one critical problem is the GNN representation. Remove the spatial information immediately. So say your task is, again, given this corner candidate, edge candidates, it's easy for us to answer. Yes, these 4 edges, 4 corners are the answer, immediate. But the once you change to relational graph representation, each node knows what the appearance of a node is, but kind of forget where I was. So where are the corners in relation to each other? These informations are gone. Of course, there's techniques that associate location information as a feature vector, called conv, or maybe more recently position encoding. But it's really difficult to reason spatial relationship by feature vector. It's much better to be done by the raster image representation. So of course, if your graph doesn't have any spatial embedding, say you want to reason certain properties of semantic graph, which does not have a spatial embedding, yes, GNN is the way to go. But if you have a spatial embedding, you have a graph structure which has a clear spatial embedding, you have to reason the spatial relationships. GNN is not great. Hope it's kind of also trivial to us. If you have to answer which corners, which edges are correct, we are just immediately stuck. It's very difficult for us to answer given this. And a few more other issues of GNN. Typically, the message passing by GNN is pairwise and doesn't have a higher order reasoning. let's say we take this feature vector in GNN, and so these are the connected the neighbors. So we use these feature vectors to update this feature vector in GNN. Usually, you construct a message by this feature vector, construct another message by this feature vector, another. We take the sum. Maybe at the best, there's a gating function to change weights, but you construct a message for each pair of the reference node and the neighbor. It's never a higher order. But ultimately, we want to look at everything, this, that, and that, and that. Then update feature vector. But that's not possible by GNN. So these are the kind of reasons why GNN does not work well, or does not work maybe at all for these tasks. But actually almost there. The fix is fairly straightforward. So instead of storing each node, a building corner or building edge feature as a feature vector, we just represent as an image or a feature, three-dimensional feature image, which is a normal feature volume in Convolutional. So for each building corner, we represent as a 4-channel, initialize as a 4-channel image. For 3 channels are just RGB image of the building image, and the last 4th channel contains the location of a corner, just a heat map style. Same thing for the edge feature volume, 4-channel, first 3 are RGB. The last channel is the edge location by the scalar image, this initialization. Now these per node feature is a feature volume 3D. So instead of MLP, we are going to just use convolution, normal convolution to update feature volumes in some way. This part is not trivial, but now everything is feature volume. So instead of MLP, some kind of convolution makes sense. And I'll talk about how to do convolution soon. But once you get the updated feature volume, you just put the CNN encoder, this, and then ask, are you correct? Are you correct? Then we collect all the edges with answer true. That's our edge selection procedure. So the remaining question is, how do you do convolution? Use convolution layer to update feature volumes, because again, the number of feature volumes differ per sample. The component has to have a fixed dimensional input, a fixed dimensional output. So usually it doesn't work. So this is how we do. Suppose we want to update feature volume for this node, reference node. There are 3 kinds of nodes. First is reference, yourself. Second kind is its neighbors, the orange ones. So neighboring nodes. And then the rest. So we just first copy this feature volume here. And then we do pooling. We do some pooling over the 3 neighboring nodes. You get that? And then for the remaining one, we again do pooling. So we concatenate and do just convolution and output the feature volume. And the trick is, since we pool, this dimension is fixed. Always 3 kinds. A concatenation of 3 feature volumes, reference, neighbors, and the rest. So we do this for every node 1 by 1. So to update this feature volume simultaneously, we again do this pooling. And then get the feature volume. And we do that for every single node simultaneously as one layer of message passing. Hope this makes sense. So we call this convolutional message passing. It's very easy to implement. And it's a 3D volume representation, contain location of corners and edges as a grid, as opposed to numeric values in the boundary vector. So allows easy spatial reasoning. Also achieve a higher order relationships learning, because we put every information into a single convolution operation. And of course, we do pooling. So this operation pooling is a bit problematic, but actually usually, say when I pool these 3 information, so this information of this particular edge is usually stored around this part of a feature volume, and this feature of this edge is stored somewhere around this part of a feature volume. So when we do pooling, information do not collide much. We are working with a 3D feature volume as opposed to 1D feature vector as in standard GNN. So our dimension is too higher. So information does not collide much. So that's also a reason why this works well. So now, given this engine, convolutional message passing, I want to present our first automated floor plan generation system, HouseGAN. It's actually easy once you have all the modules. So input is a bubble diagram, which becomes a relational graph, and each feature vector encodes a room type. And also, we generate a random noise vector. Use MLP to upsample, rearrange to a 3D feature volume. Then after that, we do convolutional message passing. So enrich feature volumes, upsample, goes back, message passing, upsample, I think 2 or 3 times, starting with maybe 8 by 8 spatial dimensions. Then later 64 by 64, somewhere around that length. So pretty low resolution still. So once we get the feature volume, we put the component and get the segmentation mask per node. So that's the generator. So discriminator is the same. So flat point is a graph of segmentation mask. So this comes here. And then again, from the MPN, message passing, this time downsample, goes back, message passing, downsample, again, the same number of times, twice or 3 times. Then we do just comb encoder. You get the feature vector, full, followed by linear layer to output true false. So pretty symmetric design. And we use this kind of a data set. The very first one project was from Life database from Japan. The second, the latest one using from Alplan database. I believe the company from China, Kujale, hired architects to make these floor plans manually. So we have this floor plan, the bubble diagram we extracted. We have a bunch of pairs. This is our input data source. And the system I just talked about. So we look at each row by row. So given this bubble diagram, it's a raw result, raw graph of the segmentation masks, and do some post-processing to convert to vector format. So looks actually kind of good. I'll skip the detailed evaluation, which are in paper, because there's one more improvement we have done. So I'll just go to the limitations of the system. Although this paper seems to produce very interesting results, but actually far from satisfactory. So actually all the room shapes are rectangles. So this doesn't look rectangle because we just sort all the rectangles and render in some order. But the real shape is everything is rectangle. And so the architecture did not understand the non-rectangular room shape. And also it could not generate doors or windows, which is actually very small. And again, training gets trickier if the resolution goes higher. So the difficulty in handling thin structure. And also shapes, row shapes, if you see here, doesn't make sense. Doesn't look like a room shape here. So there are many, many issues. We do some post-processing to kind of cheat to produce good-looking results, but network itself was not really working. So here comes the third one, which resolved all these issues. And to be honest, we don't really know why this trick works well. We really spent time trying to dig why. We couldn't really explain well. So still mystery, but let me explain what we did. So the key idea was we want to design some refinement architecture, meaning, so this is our original architecture. Given a graph of noise vectors, the generator makes the floor plan. We do some post-processing to get the floor plan. And in addition to the vector, you also allow the system to take some previous or current guess of room segmentation masks. And G makes it better refined. Now we can put it back, then run again. So generator works more like a refinement generator. So the change is only we allow the input to contain some segmentation mask in addition to the noise vector. But the training is not easy. So this type of recurrent architecture is difficult to train because if you think about how the system works, initially no design, you run generator, get some output, we pass these results to refine, finally get something realistic. So let's put the discriminator here. and train. This is very difficult because we have so many layers. And GAN training is already tricky, and this seems just too difficult to train well. So the current model doesn't offer a good training solution, unfortunately. So what we ended up doing, got some inspiration, although we realized this later, share some inspiration from the math language training. This is what people say, transformer. In their self-supervised learning task, in NLP, they do things like given a sentence, how are you doing today? So we hide certain words. Then the task is to infer the missing word. So this was used effectively for the self-supervised learning of some NLP representation. And our observation is, so we have NLP language at the left, and now we are trying to use a transformer for various image analysis tasks. But structured geometries, the floor plan, have components and connections by edges. So very similar to NLP because they have really compositional structure explicitly. So these kind of techniques from NLP should be really effective for structured geometry more than image. So what we ended up doing was component-wise mask GAN training, a bit too long and fancy, but very simple. So we do basically masking. So given takes some ground truth floor plan, we hide some room mask. So maybe sometimes I hide everything. So start from nothing and then just try to generate something realistic. This is a normal GAN training task. From nothing, realistic floor plan discriminator. But sometimes we hide, say, only this, mask only this room. We pass room and the door. So these tasks only fill in the missing information. So much easier. Or sometimes we pass everything. So G just copy everything and D should be happy. So we just mask some component, some random probability, and that's it. Very simple fix. So with some details, we mask each segment, but 50% chance at random. So actually, these tasks become easier. Often, half of the segments have a ground truth shapes given. So usually GAN training is tricky because G is difficult. D is easier. They lose the balance. They model collapse and bad things happen. But now G's task is easier because we provide the ground truth segmentation mask for many nodes. So we realize training gets more stable. And also the system allows us to refine, meaning allow us to pass previous result as input. This was kind of a big change. So overall architecture, this is our previous architecture, HouseGAN architecture. HouseGAN plus is very simple. The top portion, this part is the kind of same. Just for each node, add the segmentation mask. And for some node, we allow not to pass the previous segmentation mask. It's represented as this black image or white image. And the rest is the same, G or D. So that's only difference. So at this time, we do things like start from nothing, we generate, and say living room, bedroom, door. And we only pass the living room, do not pass these two. So this is the condition for the next round. Given this, generate, say this. And second round, we also pass door and say living room as condition for the next. And then G generates. Now everything looks good. So we pass everything, condition, and refine. So we decide which room type or which room to pass for the next round. And we have some heuristics. So we also learn some strategy by Bayesian optimization. So again, we don't know why this trick works, but actually works much better. So this is the refinement result. So input graph, bubble diagram. After first generation, we get these. So many room shapes are corrupted. Just keep refining, and at the end we get this. Or another bubble diagram, we keep refining. Usually just a room boundary becomes straight, aligned, and kind of looks like a floor plan. And the first one to show finish in about 5 minutes. First one to show the realism evaluation, which is we show the ground truth floor plan. So we show to the user these are the kind of result which we prefer. So 2 samples. Then rank which is better or the same. So if you get chosen to be better, you score 1.0. If you tie, score is 0 point. And then if the other side wins, it's -1. Sorry. Yes. So I just focus on the right one. So maybe just one, look at this number. So we are comparing against the GT, ground truth floor plan made by the human architects. So it's our generation. So score 0.18. Basically meaning that if we provide 100 comparisons, subjects which are half graduate students, half professional architects, 45%, 41% of the time they choose ours to be better. 59% GT better, which is very good, because at best it's 50-50. That's optimal. The result was very good. So here are such comparisons. So don't worry about the X and check mark. So there are 8 floor plans. 4 are from human, 4 are from our system. It's probably very difficult to tell which are human, which are from the computer, and the bottom are our results. And very good. And also architects, when they choose which is better, they really look at something very complicated. So this arrangement, the room and bedroom doesn't make sense. Well, I like maybe how you place bathroom here. So they really reason something very higher level to reason which is better. And I just want to show more results due to time. I skipped some details. We compare against any other layout generation. Usually placing objects in the image, the layout algorithm doesn't work well. And have some evaluation. This is much better than anything else. So I'll skip some details in short. So I think we have done something interesting. So the question is this useful? Is this production ready? So there are 2 big issues, missing rooms and duplicate rooms. So I showed you this slide earlier. Maybe some of you may have noticed there are actually many obvious mistakes. So typical one is, say, these 2, this is maybe 2 balconies. We see actually 3 balconies. So we cannot keep the same number of rooms. Or we say that there must be, say, 2 bathrooms, only 1 bathroom. So missing rooms or too many rooms, this often happens, which we know is very difficult. But it's easy to handle. When we do refinement, after each generation, we can check how many rooms we generate. Is that compatible with the input bubble diagram? If not, we can remove easily by heuristics. We just didn't do, because we want to really evaluate the core capability of our machinery. We didn't do that, but it's very easy to do by heuristics. So missing rooms and duplicate rooms, which are the major failures in our case, but we know how to do that by heuristics. And what's really maybe interesting is usually design requires more complicated constraints. For example, building code, or where is the node? South, east, yes.
Yes, so sorry, I don't. Yeah, we're about 7 minutes over time. If you could please,
yes.
Wrap it up. We will have more time. We have a panel discussion, as you know. So.
Yeah, sorry, yes, actually that's the last one. So I want to thank our funding sources. And again, if you want to play around, please go to the website. It's already up. Yes, so that's all. Thank you very much.
All right. Great. Thank you very much. It's very interesting. I'll have to go and check out your website to design my dream house or layout.